Hi everybody, this is week 7 video, and as we mentioned before that we are going to revise few lessons from chapter 10, which is 10.1, 10.2, 10.3, and as much as possible that we can cover by this video, we will do it. Now, as we mentioned before, if I want to identify or evaluate a limit from a given graph. Now, for example, let's say we have this graph here at this form. Let's say 1, 2, 3, 4. Same thing, let's take 4 each side. I'll say that we have the graph here as a field point, and let's take it at -2 toward the side. Just a quick example about the idea of evaluating limit from a graph, and it's applicable for any graph. Now, let's say that I want to find the limit, evaluate the limit for x approaches to 2 for f of x. Now, we know that in order to find the limit for x approaches to 2, as you can see, there are two graphs, one at the right and one at the left. So directly we understand that we have to find the limit from left and right and add 2 exactly. Because we said in order for a limit to exist from left and right and add exactly at the given number that x approaches to, all of them, they must be equal. Also, whenever the limit exists, it means the function is continuous at that given value where x approaches to. So if the limit exists, then the function is continuous at that point. Or we can say, to be more accurate, if the limit exists at a given point, then the function is continuous at that point. However, so now we will find the limit from, let's start from left, for example. So we'll say limit x approaches to 2 from left. Now from left, it means you are approaching to 2 from left. So we are coming from this side. Now, the more you approach to 2, your answers will get closer and closer to -2. So here we say answer is -2. Now, if we check from right, limit for x approaches to 2 from right for f of x. Then from the right, it means we are approaching from this side. We are getting closer to 2 from this side. It means that the answers are getting closer and closer to 2. Now, directly we know that the limit does not exist because from left and right, they are not equal. No need to check from the middle. But even though, let's find also f of 2. So f of 2, here you have a filled circle, which we will take, and here you have open circle. It means it's undefined here. So 2, it is the value of f of 2 is 2. However, but in general, limit of x approaches to 2 does not exist because, as we said, from left and right, it's not equal. So also we can say, we can merge this information with it. Also, it is not continuous at 2 or at x equals 2. Now, regarding continuity, we classify the functions according to their domain. Now, for example, continuity. Now, continuity here. Now, for example, if I have f of x is equal to any square root, let's say for x plus 8. Now, whenever you have a square root or an even root, let's say 2, 4, 6, 8, any even root, then directly the function will be continuous at where the radicand is more than or 0. So here 4x more than or minus 8, so the function is continuous only at x more than or minus 2. So as x more than or minus 2, then the function is continuous. Now, if I have an odd root, cube root, for example, or any other odd root for x. Let's take the similar to that example. So here, domain for the odd root, it will be all real numbers. So here we will say the function is continuous everywhere. Now for the last one, which is the rational, if you have f of x is equal to for x plus 10 over 2x minus 20. Then here we are going to solve only the denominator. It's like we are finding the vertical asymptote. Now we know that vertical asymptote where the function approaches to but will never reach. So that value is undefined. So vertical asymptote is the zero of denominator. So here we'll say 2x is equal to 20. So x is equal to 10. So here we are going to say continuous everywhere except at x is equal to 10. Or you can just say simply x is not equal to 10. So that means the function is continuous everywhere except at x equals 10. Now this is regarding the continuity of a function. Now let's talk about infinite limits and limits at infinity. So let's start with a graph, a quick graph. We should do this, or I have done this with the previous graph, but here we are again. Let's draw it again. No, sorry, I totally forgot to take a limit at infinity with that graph. So we will do it again. It's not necessarily the same, but we have a graph. Now, for example, if the question is evaluate limit x approaches to infinity for f of x. Now here, x approaches to infinity, it means the more you go right, your graph will more go up to infinity. So here we will say limit for x approaches to infinity for f of x, then the answer is infinity, which is positive. Now, if I want to find limit for x approaches to negative infinity, it means you are approaching from left. Now, the more you go left, your graph will more go down. So here we say the answer for x approaches to negative infinity, it is a negative infinity. And it's important to mention, we didn't get the answer minus infinity because we are approaching to minus infinity. Now, of course, as you know, the graph may go up. So it depends to the side of the arrow or of the graph. Now, let's take evaluating limit where x approaches to infinity for a given function. Now, as we mentioned before, let's say that we have x to power p over x to power n, for example, or q. Now, if the degree of numerator p more than degree of numerator, where p is more than n, then here the answer would be infinity. Now, if p is equal to n, then you have to simplify the variables you have. And the answer will be a constant. Now, if p is less than n, then the value of the limit or evaluation limit will be 0. Now, it's very important to mention that we use limit at infinity to find the horizontal asymptotes. So whenever you get an answer as infinity while you are finding horizontal asymptotes, you will say no horizontal asymptotes or none. And here, this will be the value of the horizontal asymptote. So now let's take one question, merging limits at infinity with the horizontal asymptotes. Since we are going to use the same method to find the value of limit x approaches infinity, or to find the horizontal asymptote. It's the same idea. So now here, find all of vertical and horizontal asymptotes. We say for f of x is equal to 4x squared minus 16 over 2x squared plus 8. Now here, we will start. Let's start with the vertical asymptote. Now, vertical asymptote, we are going to solve denominator if possible, of course. So here we have 2x squared plus 8 is equal to 0. So directly we'll have 2x squared is equal to minus 8. X squared is equal to minus 4, which is not possible or undefined. Now, since it is undefined, so we have no vertical asymptote. So here we'll say none. Now, for horizontal asymptote, as we said, we are going to use limit at infinity. So you say limit x approaches to infinity. And we only take p over n, highest degree with the highest degree. So here we'll have 4x squared over 2x squared. Now, as you can see, degree of p and n, they are the same. So you are going to simplify the variables, and then you'll have 4 over 2, then the answer is 2. So here we say we have a horizontal asymptote at y equals 2. Now, for vertical asymptote, you solve denominator. For horizontal asymptote, you evaluate limit at x approaches to infinity, and you compare the degrees. Now, for example, let's say that we have limit x approaches to 0 for f of x is equal to 5, and limit for x approaches to 0 for g of x is equal to 3. So, for example, find the value of x approaches to 0 for g of x, limit of g of x minus 2 f of x over f of x, for example. So here directly, either you use distributive property for the limit, or directly you can just evaluate. Now, limit x approaches to 0 for g of x is a 3. So here we say 3 minus x approaches to 0 for minus 2 f of x. And we have f of x as 5. So we'll say minus 2 times 5. Again, limit x approaches 0 for f of x is 5. So we'll just write 5 here. So here we have 3 minus 10, which is 7 over 5. So the final answer is 7 over 5. And that's it. Now, this idea is just to explain that limit can be distributed. However, now, let's say that we have limit x approaches to 0, and we want to evaluate, for example, radical 2x minus x all over, let's say, x. Now here, if you are going to use a direct replace to evaluate the limit, of course, you are going to get undefined, or limit does not exist, because once you replace 0, it is the 0th denominator as well. So here we do rationalizing. Now, as we know, in order to rationalize, you just take the radical and you multiply it with the opposite factor, minus, plus, but you take it as it is. Radical 2x plus x. And now, we are supposed to multiply. But here, as we know, we use rationalizing because it is considered as difference of two squares. Here you have minus, here you have plus, radical 2x, radical 2x, x, x. So it's considered as difference of two squares. So directly you just square the first minus square second. If you have a squared minus b squared, you can write it as a plus b, a minus b. Same thing here, the same idea of rationalizing. We are applying the same idea. Here we have, they are the same binomials, but different in sign. So you can square first minus square second. Now, when you square a radical, you will get the radicand only, minus, or let's just take a radical here to make it easier for you. Yeah. So let's say we have radical x. So you will have 2x minus x over x multiplied by radical 2x plus radical x. This one is multiplied by, now here you have 1x over x 2 radical x plus radical x. Now you simplify x with x, but however, again, once you replace 0 in denominator, still undefined. So here we'll say it does not exist. Now, why we are taking this example? Just to let you know that even sometimes when you rationalize, still the limit does not exist. Now, that was a quick summary about the ideas or the main ideas of chapter 10, which is 10.1, 10.3, and 10.2, of course. But there is one more idea from 10.2 where we have to evaluate a limit for h approaches to 0, for example. Now, limit h approaches to 0 for f of x. Let's say that we have f of x is equal to 5x plus 3. Now, to evaluate this limit, it will be given as limit h approaches to 0 for f of x plus h minus f of x all over h. Now, in order to solve this one, we will start with finding each part. Where's the minus? It's gone with the wind. So here we have f of x plus h. So directly you know that you replace each x with x plus h. So you'll have 5 x plus h minus, sorry, it was plus 3. Then you distribute. Then we'll have 5x plus 5h plus 3. And this one, all of it is f of x plus h. Now, however, let's find the second part, which is f of x. Let me take this one away. So here we have, oh, sorry, that was my mistake. Yeah. So now we will find f of x plus h, which is this one, minus f of x. So we will get, this is f of x plus h, 5x plus 5h plus 3, of course, minus the function itself, which is 5x plus 3. Now 5x minus 5x, it will be simplified. 3 will be simplified with 3. So now finally you have limit h approaches to 0. This one, all of it, it's only 5h over h. Now you simplify h with h. So finally you have only 5. Now it's very important to remind you that if you can check your answer by using the derivative rules. Now the idea that this one, we call it derivative by definition, which is the 4 steps derivative. So finally you can just check your answer by using derivative rule. Now the function was f of x equals 5x plus 3. Now if you find the derivative, a constant with x, number with x, derivative, it's only the number, which is 5. A derivative of a constant is 0, so you have only 5. So this is how you can check your answer. I hope that video summarized the main ideas for 10.1, 10.2, 10.3, and hopefully next week we are going to do a video for the chain rule in derivatives, which is chapter 11. Till that time, stay safe, take care.